Great, we are going to be solving nonlinear systems. That means we're going to have two or more equations. Some might be lines, some might not be lines. We're going to be solving it with both graphing and with algebra. And I'm going to start off with graphing, and that really just means graph all the equations. In this case, there's only two. We're only going to be using two. And we're going to be looking to see where those two equations cross. They might not cross at all, so we'll have to be considerate of that as well. The first equation I have is a parabola. So I see this whole quantity being squared. It could be, this happens to be in vertex form. It could be in standard form or intercept form, but just as a quick review of our vertex form, whatever is being subtracted from the x is our x coordinate, and then whatever is being added outside is our y coordinate of our vertex. So our vertex is going to be 4, -4. So remember, opposite sign inside of the parentheses, same sign outside the parentheses. And our a happens to be 1. So you can plot that point for -4. If you don't have graph paper, just a sketch of the XY axes and tick marks are fine. And then from here, if you want to use your stretch factor, great. You're going to make a horizontal move, square it, and multiply by a. So 1 squared is still 1 times our a of 1 is 1. So a positive 1 means goes up. If it were a -1 squared for my horizontal move to get a positive 1 times my a of 1, I still go up 1. You could do that again. So how about I do a -2 squared is going to be 4 times our a of 1 means go up 4. So 1, 2, 3, 4 right on the x-axis. So we're not looking for the x-intercepts or the solutions of the parabola. Instead, we just want to make a nice accurate graph. So you can plot using the stretch factor. You could also make a table of values. So here are the same points I just plotted. I'm going to go ahead and reflect this over. When we go over 2 to the right, we'll go up 4 as well. So 2 units over from the axis of symmetry. And you can make more points if you want. It's important that you make the graph be as accurate as possible, because if we're just going to look to see where these two equations are crossing each other, we want the two equations to be plotted as accurately as possible. So I'm going to stop my graph or video just so I can make my graph. So I may not be expecting perfection on your parabolas, but I want enough points that you can graph an accurate parabola. 5 points is usually the barest minimum I would say you would want. My next equation happens to be a line. I don't see anything squared, just an x, and that looks a lot like slope-intercept form, one of our best friends for graphing. And that means that our slope then would be -6 is being multiplied by x for our slope. And it's always nice to think of slope as rise over run, so -6 over 1. And our y-intercept is the constant being added of 11. This graph does not go all the way up to 11, and that's totally fine. You can either estimate, so here's my 8, 9, 10, 11. Notice I'm not going to draw on all the extra lines. And then from there, you could use your slope of -6 over 1. If you don't want to go off the grid that far, you can, of course, make a table of values. So if I were to plot just a few points, I could also just pick some x's. When you have a line, remember, you can pretty much pick any x you want. There's no vertex to look for in the line, so I'll make that table in a second. But first, from our slope-intercept form, the 11 being our starting point, always on the y-axis, and then from there, I'm going to rise -6 and run 1. So make 2 moves for my next point. So if I go down 1, 2, 3, 4, 5, 6, and over 1, ooh, look at that. Looks like I'm hitting the parabola. And down 1, 2, 3, 4, 5, 6 over 1. I'm just to the side of the parabola. So I'm going to go ahead and use a straight edge. So again, try and be as accurate as you can. A piece of paper or a ruler would be great to graph that line. When you're graphing these functions, please try and label the two functions. So here I labeled my equation of the line and the equation of the parabola right next to the ends, and try and make the equations that you graph go all the way through the graph, because you never know exactly where they're going to cross. When you're looking for the solution, if it's your own graph, you might have to estimate that solution, but it does look like they have this one exact point in common. So if I look at 2, -1, where I plotted my next whole number of points for the line, I couldn't possibly have a parabola point right there because I'm at 2, 0 on the parabola, so I can't also have a 2, -1 on the parabola. But also it looks like they're kind of crossing again above this point here, but honestly, think about a curve. That curve can't curve back again. It's opening wider and wider. So that means the line is on the left of the parabola here. They cross at one point, and then the line is on the right of the parabola for the whole rest of the way. And so that means this one coordinate is our solution. And if you have to estimate, do your best to estimate. If it's given to you on a graph, usually you don't have to estimate much at all. So this looks like 1, 5. So always give that solution as an ordered pair with your x first and then your y. When you're looking at different functions that could be graphed, here are some very general cases that don't have any grids to go with it, so we're not actually estimating the solutions, but I want you to recognize that you have lots of special cases to be looking for. So the one that we were looking at, we had a line and a parabola. They crossed once. In this general picture, they're crossing at the vertex. The way that we had it, it graphed or it crossed somewhere on the edge of the parabola. But they could cross just one time. It could be that the line might never cross the parabola at all, or it might cross in two places, but there's no other way you could draw a parabola and a line and have them cross more than twice. If instead we had two parabolas, like these examples here, those might never cross at all. If they're opening opposite directions away from each other, they might touch just at the vertex, or if you were to scoot one up further, they could cross twice. But now if you imagine any other parabolas, even if they're open the same direction, the most that they could ever cross would be twice, and the fewest would be none. With a circle. So we're not going to be graphing circles today, but I do want you to at least recognize what it might look like visually. So if we had a line and a circle, we won't do anything more complicated. It's possible that line just goes somewhere way far away from the circle and they're never going to cross. They might just cross once or they might cross twice, but there's no way to have a line cross a circle more than twice. Now, as far as what this looks like if we were to graph it or looking at the equation is going to look a little more complicated than a parabola, that we're going to have squares in both the x's and in the y's. So there might be something inside the parentheses with each of the quantities being squared, but the r is going to stand for the radius of the circle. So that'll be a number. So a radius, again, from the center out to the edge of a circle. So if I were given an equation, maybe it was an equation that looks like x squared plus y squared equals, say, 4. Now that means this is the same as having 2 squared. That means the radius of my circle would be 2. So from the center, because I'm not shifting left or right at all, there's nothing subtracted from our x's or y's being squared here. From my center of 0, 0, I would just go out 2 units in every direction, left, right, up, down, and I'd get, say, these 4 easy points, and I could make that circle. But again, we're not actually graphing. Just wanted you to see what it would look like. But do keep in mind that when you have squares in both x's and y's, our equations are going to be a little bit more complicated to deal with.